OCR A, A-level physics. This is my second video on medical imaging, and it's about using radioisotopes. So basically, the patient is injected with something radioactive. The substance collects in certain organs, and then it decays and it produces gamma photons when it decays, and then you detect the gamma photons to produce some kind of an image, so using a gamma camera. The most commonly used isotope is technetium or technetium. I call it technetium 99M. It's called. It's got a half-life of 6 hours. When it decays, you get gamma photons and low energy electrons. So the electrons don't do a lot of damage. The gamma photons can easily leave the body and can accurately be detected. And then the isotope can be combined with a wide range of biologically active substances. So it can be used to target a range of organs. For example, if you want to target places where a lot of respiration is taking place, you might attach it to some glucose. Yes, you can target specific organs. 6 hours, that's long enough to take good images, but it won't do long-term damage. So you don't want the stuff lingering in your body for days and days, because it is producing ionizing radiation. A little note as to how hospitals actually get this stuff, and they use a generator, a molybdenum technetium generator, which is another substance which decays to produce technetium, and this generator lasts a couple of weeks, and they send it off to get loaded up with some fresh molybdenum, so they can the hospital can produce the technetium when they need it. The gamma camera, we need to know a bit about how this works, different bits of it. So starting at the bottom, you've got the x-rays have gone through the patient, then they go through a collimator. Now the collimator is lots of lead tubes, and the idea is that we want only the gamma rays which are kind of traveling parallel to the axis to get through. So the ones of which have been scattered, which are going off in weird directions, will be absorbed by the lead, if you look at the diagram. So a collimator produces a parallel beam of x-rays. The scintillator produces flashes of light. So it absorbs the x-rays and you get flashes of light, and then photomultiplier tubes, and they convert the flashes into electricity, an electrical signal, but also multiply the signal a great deal. How do they do that? Well, using this thing here, this photomultiplier tube here, and you can see that we get a little bit of photoelectric effect at the photocathode. Those electrons are accelerated and they bash into other electrodes called a dynode, and that produces more and more and more and more electrons, till eventually at the final anode you get a big burst of electrons, so you get a strong signal. Yes, this is a photomultiplier tube. Positron emission tomography. Okay, so positrons, if you look at the equation there, fluorine 18 decays, and one thing it produces is a positron. And that positron almost immediately will annihilate, it will hit an electron, so you've got antimatter and matter, and you'll get two gamma photons emitted in opposite directions. And then you can detect the gamma photons, yes, and figure out where all of this happened. Yeah, both photons are detected, and from the time difference, the computer can actually work out where they were produced. And so you get lots and lots of information, again in slices, so it's tomography, and you can create a 3D image. The computer can, like the one below. Fluorine 18 is apparently the most commonly used for PET scanning. You attach it to, for example, you attach it to a glucose model, a molecule, to study, again, lots of respiration places. It's got a half-life of about 110 minutes, which makes it very suitable for this kind of thing. And this technique produces high quality 3D images, excellent for looking at soft tissues, but again, the machines are very, very expensive. So sometimes hospitals have to make difficult choices.